Well, I'm going to model a series of scenarios that result in a explosion on a coal mine, and that's quite a frequent event, unfortunately. There are a number of reasons why you can get that, but the most common one is the collection of flammable gas resulting in a gas explosion and then igniting a much stronger dust explosion. I've loaded the mine shaft plan, and so the idea here is that within this shaft here there is a release that takes place due to the failure of the ventilation system in this region. So I'm going to go ahead and start to model it. I'll just pick out these regions here. Of course, I don't want the hatched area. I just want that line in the middle. That represents the surface of the shaft that is releasing the methane. And so I'm going to assign it as a release inlet. Before I go any further, I need to put in the dimensions. So the dimensions here are 340 by 484. And we'll use a cell size of 0.8. Recalculate, apply, and close. Put in an analysis instance. Okay, to set up a dispersion simulation, all you have to do is just select dispersion, and we need to put in the expected mass flow rate. We estimate, or we've been told that the estimated mass flow rate in kilograms per second is 0.1 kilograms per second, and here the release panel is 100 meters. This value is actually quite high, so you may get, the cloud may be rich actually in some portions, but it obviously works for any release rate. And that's all you need to do for the dispersion calculation setup. We'll put a time step of a second. So this is 3,600. I'll put in a CFL of a non-zero CFL. That's all you need to do. So what we're going to do is model the emission of methane within the shaft and the accumulation and dispersion, if any, within this shaft. And we're going to see what kind of gas cloud we have. If a portion of that gas cloud is above the lower flammability limit and below the upper flammability limit and collects in this region here, well, this is where ignition sources exist, and so that gas cloud can then ignite, cause a gas explosion, and then from then on, if the pressures are high enough, and they will be higher than what you normally get for just a simple methane explosion, because this is a highly confined region. And if they're high enough in this area here, arising from an explosion here, then there is the potential to kick up some dust, some coal dust, and ignite it and result in a much stronger dust explosion. If you didn't follow that, just stay with me and you'll see these steps as they occur. So I've done everything I need to set up the first portion of this, which is modeling of the methane release. Again, the methane release is due to a failure of the ventilation in this shaft. So in other words, it's a methane accumulation more than a release. And then we're going to take a look at the results and see if we have a flammable gas cloud. If we do, we're going to ignite it. And if the pressures are high enough, we may have to model a dust cloud as well. So I'm going to perform analysis, and we'll see you when we get back. Okay, we've loaded the results of the dispersion, and you can see the accumulation of the methane here. We'd like to take a look at the results in a little bit more detail, so I'm going to plot a line. I'll plot the release concentration over a line and just adjust it so that we can see. Now what happens with these lines is sometimes these can become non-zero. If they do become non-zero, then you're not going to record anything on the line, so just pay attention to them. If they change, then make sure that they are zero. I'll go from here to here, and yeah, that'll do. So we'll apply and we'll take a look at the concentrations. some error messages that are not relevant to us, but we want to look at the release volume fraction. And you see the release volume fraction here, well, the flammability limits for methane are between 5% and 10%. And so a significant portion of this line here is seeing between 5% and 10%, particularly in this region here. And that will ignite. So what we'll do now is go back to exploCFD and model an explosion of some gas that sits in this region here and see what kind of pressures we get. Okay, we're going to convert this simulation now. We're going to do a gas explosion simulation with a portion of the gas cloud that's about here. Okay, so the first thing I'm going to do is I'm going to deselect this as a release inlet. We'll convert the analysis into an explosion. That's the default, so I just deselect everything. I just need to increase the confinement because this is occurring obviously in a mine shaft. It's quite confined. And the other thing we need is the fuel mass, and we need to calculate that. So what I need to do is I need to first move the analysis point over here because that's going to serve as an ignition point now. And I'll go custom gas cloud and I'll just place it in here. That should be about right. And so that's this thing. Let's measure this thing. I think it should be about 25 meters. Yeah, it's about 20 meters. And so we need to calculate the volume or the mass of this thing. Now the mass of this thing is the volume of the fuel times the density of the fuel, and it's methane. So the density of methane is 0.65 at 101, 325, and 300. But how much of this is methane? It's a stoichiometric gas cloud, remember. And let's pull up a calculator. First thing to do would be calculate the volume. And of course the diameter of the shaft is 10 meters, so it's the diameter squared times pi over 4. So 10 times 10 times pi times 1 over 4. That's the cross-sectional area times 20 meters, which is the volume of the cylinder, 1,570 kilograms. How much of this is fuel and how much of it is air? Well, the ratios are in here. You can calculate this by looking at the balanced equation, counting how many moles. But by volume, there's 9.52 moles for every mole of methane. So the methane by volume is 1 over 10.52 of this volume, 10.52. That gives you 149 meters cubed. Just multiply by density times 0.65. That's about 97 kilograms. So it's just going to go 100 kilograms. It's a very small amount of methane, okay? And if this was outside, it would produce nothing. If this was out in the open, it would produce nothing. But it is confined, and so you may get high pressures. Particularly anywhere along here will kick up some dust, and so we'll run it just enough to see if we got high pressure over here, because the longer it goes, the higher it attenuates. I mean, I know there's reflections, but the longer it goes, the more it attenuates the pressure wave. So that's it. That's all it takes to set up, of course, the time step. I've set the time step to a millisecond, and yeah, let's just go 3,500. And yeah, that should run for nearly 3.5 seconds, and that should be enough to take a look at the pressures over here. So I'll perform analysis and we'll see you on the other side. Okay, we've pulled up some results. Let's apply and take a look at what they look like. Let me calculate the overpressure and take a good look at the overpressure. This is the last time step that we captured. We stopped at midway. What do we got? I think it looks like we have, let's see here. We've got at least half a bar here, so I think the color scheme is not very conducive to accuracy, but this might be better. Okay, so about 0.2 bar. So that's more than enough to cause dust to be kicked up, and you're going to get a dust cloud everywhere. And if there's ignition sources anywhere, and the gas itself is probably hot enough, it will ignite that dust cloud. So we have to go to step 3. But before we do that, let's just take a look at our gas explosion. So this is the pressure, and you could see you got a significant overpressure here. You got maybe 4, maybe 6 bar, and you could see the shock wave or the pressure wave sort of propagating through the mine shafts. And if you keep going, it'll come out the other end. But it certainly has shown that it looks like we need to model a dust explosion that would probably ensue from this. And so we'll go back to exploCFD and set that up. Okay, so let's set up a dust explosion. We're going to set up a dust explosion in this region here. Okay, so first of all, I'm going to remove the gas cloud. So just click on here, go custom, and remove it. And we'll go to a dust explosion. So just select dust explosion here. The KST for coal dust we're going to take to be about 85. The radius is 10 meters, obviously, and the dust laminar velocity, well, that's close enough. So go custom gas cloud here. So that's how easy it is to set up a dust explosion. So remember, we started off with a dispersion of methane, then we did a gas explosion of stoichiometric methane, and now the sequence of events has resulted in us having to model a dust explosion. Sometimes if you slip out of the boundaries, it's easy to go back in and go, So that's a dust explosion. Cancel, Q for processing, and away we go. And we'll let that run, and we'll go back and look at the results for the dust explosion as well. So here we go. Okay, now SU2 is finished and it's called Opera View, and we have some results for the dust explosion. Hopefully we'll pull up the overpressure and go back to the initial time step, and so that's what we have. Let's change the scale. Let's take a look. So the scale, yeah, you could go from like 100 pascals. You don't really care below that. So you can see the maximum pressure here is significantly higher than the 4 bar that we had, or 5 bar that we had. We now have 1.3 megapascals of pressure, and that's typical because the dust explosions can be very powerful indeed. All right, let's take a look. We'll run through this. So obviously this is going to cause immense structural damage here, and the overpressure is expanding. You're still seeing over a bar everywhere here. So anyone in this region will unfortunately be killed. Up here, we said we're looking at the case up here. It looks like we're getting 0.2 bar up here. We're getting half a bar coming out of the shaft. It's green, so green. So in this region here, you might have 0.1 bar, 0.1 bar, between 0.1 and 0.2 bar, I'd say 0.15 bar. We'll have a closer look at the pressure. You can see what the shock wave is doing up there, and just as the pressure is coming out of the other shaft here. And that's it. So let's just plot some overpressure on a line here. Some overpressure on the line. So I'll go data analysis, I'll go plot over line, and we'll go from here to here. Okay, that'll do. Just important to make sure that these two numbers here are 0, because we're we've got two-dimensional calculations. Otherwise you get no results. And so if I apply, and all I'm looking for, I don't care about the other stuff now, all I'm looking for is the overpressure. So I've got 8,000 pascals, so that's under 0.1 bar. That in itself won't kill anyone. So unless there's structural damage here, which this can maybe can cause, then I think people would survive. But let's see if this is the maximum that you get. So we really want to sort of animate it over time. So go back. So initially it's 0. Obviously the pressure hasn't arrived here yet. And then we'll move on. Next one. Nothing yet. And then when the pressure wave arrives, had to press the wrong button. Pressure wave arrives. So now we are looking at 7,000 pascals, 0.07 bar, 0.13 bar, that's a maximum, 0.14 bar, and it looks like it's peaked and it's about to drop off now. Yeah, it's about to drop off. So 0.14 bar. 0.14 bar pressure isn't enough to kill people by itself. However, it is sufficient to cause structural damage in this region, which that in turn will definitely kill people. So what you would learn out of a simulation like this is what to look out for in terms of a dust explosion, rather than so perhaps the mitigation measure would be, if possible, to design this to withstand 0.2 bar, if that case was unavoidable. But that's basically it. That's how to model a mine explosion. It's a complex process, but it's easily doable on exploCFD. These calculations took tens of minutes each. That's the advantage of using something like exploCFD, and you get pretty localized results, and you could go through the dispersion, the gas explosion, and finally the dust explosion. If you have any questions about exploCFD, feel free to contact us. That's our contact details right there. Thank you.